We will continue with section 4.9 in the book, which was talking about the reduction of a simple distributed loading. So 4.9. Now we will be discussing a very interesting example today. This is problem 4156. So 156 in chapter 4, this is a problem. The problem is showing us a beam and over which there is a distributed loading in this way. Now, you could see that we have distributed loading, we have point or concentrated loading here, and then we have moment at point O with a value of 500 kilonewtons meter. The dimensions of the beam are given as 7.5 meters to this point and 4.5 to this point. Now the question is asking us to replace the loading by a single resultant force. Now the loading, that means we have to replace this distributed loading, the point loading, and the moment by one single force, which is the same thing that we used to do back in 4.8. So how do we think in such situations? First, we need to convert this distributed loading into concentrated load or loads. Now, as you can see, actually, this distributed loading has the shape of a triangle, right? So two triangles. And as you probably remember, we said that the concentrated load arising from distributed loading is basically the area under the curve. So now, since we have a triangle, then the concentrated loading F, or the point loading F, is simply the area of this triangle. Similarly, for this triangle as well. So now, let's work on these triangles one by one. So now we know for a fact that we will have a concentrated loading here, another concentrated loading here, and then a third one over here, and a moment. So we have to sum up these three loadings to get one final resultant force and moment. And then we need to replace the resultant force, the new one, plus this couple, by one single force. So first, what we need to do is just work with the triangles one by one. So let's take the first triangle, this triangle, or the first one. So this triangle basically has a height of 6 kilonewtons per meter, 6 kilonewtons per meter, and a base of 7.5 meters. So from this triangle, we know that the force is basically the area, which is the area of the triangle. So it's half the base multiplied by the height. Right? So this is 22.5 kilonewtons, and we know for a fact that it should be directed downwards. Now, one very important point is to find the position of this concentrated loading. Now, from the previous problem that we solved together, we saw that basically the area is concentrated here, and we said that the force is usually should pass through a point that we called centroid. So this is the centroid. We will be discussing centroid in more detail in chapter 9. Anyways, so as you can see, here we have more area as compared, or actually the force is concentrated to the right? It should be concentrated to the right because we have larger height here. So probably this portion should equal to this portion. Hence, the force should be shifted a little bit to the right. Now, since we don't have an equation here that from which we can actually use to come up with our centroid, then we will see in the later or in chapter 9 that some basic shapes, they already have known centroids. For example, for this triangle, the centroid for this triangle in this direction, let's assume this is the height. So in the height, it's h over 3. And in this dimension, which is the base, if you call it b, then the centroid should be located at 2b over 3. How did we come up with that? We will be discussing that in detail in chapter 9. Anyways, some basic shapes have known centroids. So now what do we care actually about is the x component, right? The x component. So for us, if we had a force which should be concentrated here at this point, we don't really care about the height. We care about, or the y component, we just care about the x component. So from here to here, this is x bar for this force. Let's call this force F1, and let's call this distance x1 bar. X1 bar is simply, this is the base, right? 2 over 3 multiplied by the base, which is 7.5. 2 over 3 multiplied by 7.5, this is 5 meters. So our concentrated loading or load for this first triangle has a value of 22.5 kilonewtons pointed downward, and it's positioned 5 meters from point O. Now we go and work with the other force in the same, or other distributed force in the same manner, right? So here we have this force, distributed force. The height is exactly the same, 6 kilonewtons per meter, and this width is 4.5 meters. So F2, it's called F2, is also the area of that triangle, which is half multiplied by the base multiplied by the height. So this would give us 13.5 kilonewtons, also acting downwards. Now we need to find the position of the force as we did, or the concentrated force, right? The position of the concentrated force as we did in the first triangle. Now, so basically, what we will find now from our equation, this one, x2 bar equals 2b over 3, 2 over 3 multiplied by this distance, right? This distance, the base multiplied by 4 over multiplied by 4.5. This would give us something like 12 point. This is So this is actually 9 meters. 9 meters, right? This is 9 meters. No, I apologize. 2 multiplied by 4.5, this is 9 over 3. So 2 multiplied by 4.5, this is 9 over 3, this is 3 meters. Now, this is 3 meters. 3 meters from where? From this point. So 2 over 3 multiplied by the base. So 3 meters from this point. So 3 meters from this point. This is 3. So it would be concentrated somewhere here, for example. Somewhere here. So this is 3 meters, but we know for a fact that the whole length is what? It's 7.5 plus 4.5. This is 12. 12 minus 3 gives us this distance from here to our point of interest, which is 9 meters now. This is 9 meters. Sorry for the confusion. Anyways, now we calculated this distance, which was 3. But what we care about is basically the distance from point O, right? We're taking point O as our reference. So the whole thing is 12 minus 3. This is 9 meters. So x2 bar from point O equals 9 meters, right? Okay. So we found both the forces, which are the concentrated forces for these two triangles, and their distance from point O. So we could actually draw it now like this. So now we have we have moment here with a value of 500 kilonewton meters, and then we have at a distance of 5 meters we have our first concentrated force here, which was F1. It was 22.5 kilonewtons at 5 meters, and then we had the other force, which was 13.5 kilonewtons at a distance of 9, right? 9 from point O. And then we have the last force, which was concentrated force here of 15 kilonewtons, right? That's all we had, I guess. So 1, 2, 1, 2, 3, 4. So 4 kinds of loadings. Okay? Now, from these 3 forces, as we've learned before, we need to find a resultant force. Now, that resultant force that we will find, multiplied by the distance from this new resultant force, would equal to the moment caused by all these forces plus the couple moment. That's what we discussed before in section 4.8. So, again, we need to find the resultant force, the actual resultant force. Let's just use another color. So the actual resultant force now, assuming going down is positive, is 22.5 plus 13.5 plus 15. This is 51 kilonewtons downwards. Okay? Now, this force, 51, multiplied by the distance, it should be somewhere on the beam, probably not on the beam, as we will see later. So it should be somewhere here at a distance of x or x bar from point O. This is point O, right? So that force, so now let's just write it down. So the resultant moment around point O equals to the summation of moments of all the existing forces. Now, this resultant comes from this resultant force. So this is Fr, right? Fr, which is 51. Let's assume it should be acting downwards, right? So if it's acting downwards, then it would cause clockwise moment around point O. So this is negative. So negative 51 multiplied by x bar, which is the distance. We don't know where F actually is, right? It could be here, it could be here, it could be here. So x bar is the distance from point O. Now equals the summation of moments of all the forces and existing couples as well. So now the first force, this is 22, but it should be negative. So minus 22.5 multiplied by the distance x minus 13.5, and careful, negative, not because the force is going downwards, no, but because this force is causing a clockwise moment around about point O. So minus 13.5 multiplied by 9, minus 15 multiplied by 12, so this point is 12, right? We said this is 12, the whole length, multiplied by 12. Also, we have to add this existing couple, minus 500. Now, once you solve for x bar, it will give us some interesting value. X bar says it should equal to 17.92 meters. Now, this is confusing, right? Because, well, 17.9 is even larger than the length of the beam itself. So this actually means that if we had our beam at a length with a length of 12 meters, then to have a system which is equivalent to this one, the actual length of the beam must be extended. This is from my own understanding. It should be extended to at least 17.9 meters. And here we apply our resultant force, which is 51 kilonewtons. So now this system should be equivalent to this system, right? So now we have only one force, one resultant, no couples, no other forces, no distributed loading, nothing. So the beam with a length of 17.92 meters, right, and a point loading of 51 kilonewton is equivalent to this initial beam. Okay? Try to solve it yourselves again. There are several important examples actually in the book. You could try and solve yourselves. Basically, the idea is the same everywhere. And the examples that are solved in the book, please go through them. Very simple. Examples for 21, 22, and 23. Thank you very much, and I hope you understood. If you didn't, just send me an email or text me to Teams. Thank you.